very glad to visit TERI University this time and give a talk. This is my third trip to Delhi. The reason I come to Delhi for a few times is because now we're working. I mean, University of Virginia, working with the Delhi Jail Board to clean up the Najib drain as a major tributary to the Yamuna River. Okay. That's why I'm here this time. But I first visited TERI University last July. So this is my second visit. The first time we give a talk. The topic today is estuarine modeling of eutrophication and toxin. Now, I'm sure you all know what eutrophication is, correct? Right? Okay. Now, we talk about models, water quality models. Okay. What is a water quality model? Water quality model is with input sources such as contaminants, pollutants, enter into the system. So today, our system is one of the many estuaries, right? Then the response. This input system output, you see the sequence. And in this sequence, so you see the pollutant coming out. This is the system, and what's response? And mathematically, this is what we do. Surprisingly, you see, the model only has one equation. This is the equation. That equation is based on mass calculation. That is very basic and nobody can shake it. It's like a big elephant. You cannot shake it. Yeah. How can you violate mass calculation? You can't, right? Unfortunately, there is only one equation. All the other things, the three components, J, what's that? Mass transport, movement. R, kinetics, reaction in the system. T is from one phase to another transfer. And then the input, that's the pollutant loadings. That's good. That's it. That's very simple. So obviously, this simple equation cannot do much for us, right? For example, how do we do algal growth? We talk about eutrophication. Algal growth, well, we have to learn, but we have learned from scientists how to grow algae with natural environments. Then we implement that into this system. So what I'm saying is, this is the equation. We have solid foundation. Anything after that embodies some empirical nature. For example, algal growth, I just mentioned. Yeah. How it grows, what is the growth kinetics? We learn from scientists. But there are certain degrees of empiricism there. Because of that, data, real-world data, to check the model result is extremely important. Take a look at some temporal complexity. We can have combining steady-state models, quasi-dynamic, eventually to dynamic model. Steady-state, that doesn't change, is high, and then all the way to real time. In that case, we need hydrodynamics, very complicated hydrodynamics. Okay. Now, spatial discretization. This is one-dimensional. This is one-dimensional vertically. This is the surface. Now, this is two-dimensional, and this is actually three-dimensional, right? And they become more and more complicated. This is 1, 2, and 3 dimensions. I'm not going to. I'll give you the basic concept of these temporal and spatial variations, but we're not going to spend a whole lot of time. Rather, I would like to present you the case studies so you can see more and learn more from there. First, let's take a look at the eutrophication kinetic process. Remember, I talked about phytoplankton growth based on temperature, light, and nutrients. Phytoplankton death, phytoplankton settling. When they die, they settle into the bottom. Now, this is a simple illustration. Phytoplankton, algae, take all these nutrients and light. As the growth rate characterized as function of temperature. Maximum growth rate times the discounts. This 3 x's discounts. They're from 0 to 1. Okay? 1 means no discount. 0.5 is 50% discount. Why do we have discount? That is when you're not in optimal light, you take discount. You're not have optimal nutrient concentration, you take discount. The maximum growth rate is when all these x are equal to 1. That is, we can do it in the laboratory. In the laboratory, we provide all the light we need. We provide all the food they want. And we provide the optimum temperature constantly. That's how we can measure the maximum. But then natural environment start to change these from 1 to less than 1. That eventually multiple together, that is the maximum. That is the actual growth rate. So in a nutshell, like this. But light effect, we go through quickly. Light, surface light, exponential decrease through a KE, that's light exchange coefficient. Why? Turbid water, blocking light, attenuation, light attenuation. So, in fact, the other day I'm talking about we're talking about the cleaning up the magic out the drain. Do we worry about eutrophication in the drain? No. The water is black. There's no light. Now, light effect also depends on any species. Light intensity, there's maximum optimal 1.0 here at certain light intensity. Now, this curve is germane to individual agrospecies. Also, the light we have sunrise, sunset, right? Analytically, we can represent it this way. Now, we're going to put these 3 things together. Depth effect, optimal light effect, and temperature at 24 hours effect. End up with this expression. This is exponent. That is surface light average. That is surface light. What is surface light average? Go measure the radiation outside. Okay. The easiest thing is go to the airport. Get their reading, right? For example. Yeah. What is IS? IS is, this is IS. Speaks germane to individual species. Interesting thing is, what's the 2.718? That's E. That's that little one. This is after double integration. H is the depth. KE is the light extinction coefficient. K, light extinction coefficient, what's the unit? Per foot, or per meter. Times H become a dimensionless number. Obviously, it's the dimensional. This is the dimensionless number. After all the number we plug in, this is definitely less than 1. Less than 1. Not at the optimal. H times KE. If KE is high, relative speaking, KE is high, means what? That's turbid water. Turbid water, if the denominator is high, this is going to small. Sure, they give you bigger discount on growth. If the water is deep, another factor, right? So it's easy to grow algae in shallow water. The physics is well explained in here. Okay. Nutrients, another factor. This is the concentration of nutrients. This is the optimum growth maximum. Follow a almost linear and then curved up until optimal. In this fashion, this V represented nicely in this. What is S? S is the actual nutrient concentration. For example, orthophosphate. Okay? Km is associated with that particular algae or phytoplankton. You see the interesting characteristic is here. When S equal to Km, this is 1/2. So therefore, this Km is called a half saturation constant. Half saturation, right? It's exactly 1/2. Also interesting, you can see this curve. Become curved at high concentration. This area really explains a lot. Particularly, let's say our current concentration of a certain nutrient is that. That's almost 0.95. Then we implement control measure. Reduce the phosphorus load. It most of the time reduce from here to here. A big deal. So what? You need to see effect, impact. You're not going to see any impact until you move along this curve, until this one. Then you can see the effect. Unfortunately, this number, for example, for phosphorus is very low. Very low, that will be a long journey from here to here. Right? So I will introduce this concept. You'll see them later, one by one, in the example. Nutrient recycle. That's algae eat up all inorganic phosphorus. This is organic phosphorus. This is recycled. Organic phosphorus also separate. Organic, inorganic, through this. Nitrogen, a little bit more complicated. Nitrogen, we have ammonia and nitrite together. The ammonia also have this. Ammonia is not 100% ionized. Right? Of course, they dissolve, no problem. They're not 100% split into this. So there's portion of it, each other. Yeah. So, but they all taken up by phytoplankton. And then the organic, just like the organic P here, okay, also have sediment. This line is a water-sediment interface. Water-sediment interface. Since nitrogen, inorganic nitrogen has two components for algae to use. One is ammonia, the other one is nitrate. Which is more, which is less? Interestingly, algae has some preference. We like to eat ammonia first. So this is a plot based on, it's called ammonia preference. From 0 to 1, of course, 100% is 100% of organic nitrogen coming from ammonia. If this is 0.4, that means only 40% of the nitrogen needs from ammonia. The balance 60% from nitrogen. So this is the three-dimensional plot. Okay. Now, more complicated. These plots have its definite location, but this one only germane to one situation. Another situation can be different. That means another situation could be the 200 starts from here, the 100, 50, 25, and 10. You see what I mean? But that's okay. We have simple analytic expression to describe this effect. That means we can easily put that formulation into the model. No problem. Phytoplankton death. Death has two parts. Endogenous respiration is self-respire, and the other one is grazing by zooplankton. the animals. Endogenous respiration is important because during the night, with no sunlight, they respire and cause them biomass. Settle into the bottom. So these are basic parameters. Now let's take a look at the one example, estuarine example. This is the Chesapeake Bay, the largest estuary overall in North America, but it's completely in the United States. And we have been working on it. We, not just our university, many institutions, worked together in the past 35 years. We have extensive data. You can see data rich in this case. This is the main tributary, and then on the left-hand side, I have 5 or 6. Now, that's very small, but let me tell you, this is Baltimore Harbor. You probably heard about Baltimore Harbor. Now, the major inflow, freshwater flow coming from Susquehanna River, then Patuxent River, Potomac River, Nations River, that's Washington, D.C. is. Rappahannock River, York River, James River. James River coming up Richmond, that's the state capital of Virginia. Going further up, that's what our university is in Charlottesville, Virginia. All these dots are what we call a monitoring station. As you can imagine, this is super data rich. So many monitoring stations for over 40 years of data. Not only that, in the deeper water stations, we also measure vertically. All right? The nice thing about this, all these data is publicly available. Anybody, you have the time, you have the storage space, you can link up and download all that. Now, let's zero into Patuxent estuary. This is Patuxent. From the mouth to here, about 100 kilometers. That's where tidals actually ceases. No tides. Yeah. Usually, below this, there's a certain section that's already fresh. Fresh means suddenly very low, just like fresh water. So this, we call it tidal fresh. What is the problem of this estuary? Right here, very shallow, so we have a lot of algae. This is called the Nottingham. A lot of these names are from British in early days. Chlorophyll is an indicator. It's an indicator of the biomass, so we use that to represent the level of phytoplankton. When algae move it downstream, going downstream in their direction, this becomes much deeper. They settle. The dead algae has what? Dead algae growth is fixing inorganic carbon into organic carbon, right? Inorganic carbon is what? CO2, plenty in the air. But they also definitely need phosphorus and nitrogen to grow. You're not going to control carbon, impossible. So much CO2 in the air. So when they die, in their body, they have carbon, they have phosphorus, they have nitrogen. It is the carbon when they die. They decompose. When they decompose, they consume oxygen. So this area, deep pocket, we have oxygen depletion. Very pronounced oxygen depletion. So you can see here, there are two so-called water quality endpoints to talk about in eutrophication instances. One, excessive growth of algae. Another one is the secondary endpoint, oxygen depletion. These two things we try to avoid. The timeline here is from 86 to 96, almost a little bit over 10 years. This plot represents the total phosphorus loading into the estuary. That primarily from wastewater treatment plant. This is the upper estuary, right here. This is the watershed of the estuary, very narrow, okay? Yeah. And this is nitrogen. You see, in 1986, the state imposed phosphate detergent ban. So right now, there's no phosphate detergent can be used. So that suddenly dropped the loading amount. This is kilogram per day. Quite a bit. Subsequent reduced small, albeit small, but it's due to the improvement in wastewater treatment. Nitrogen, there was no control until in the 90s we implemented biological removal of nitrogen. So you can see that. However, biological removal control subject to temperature. In the wintertime, that's wintertime. Wintertime is low, it's high, because that nitrogen removal process does not work. But that's okay. Wintertime, low temperature help to grow algae, right? Now the effect, chlorophyll A Nottingham, right here. Year by year. This is the summertime. Dissolve oxygen, yeah, the high here match the low here. All these are true data, actual data. This is the surface, this is at the bottom. Statistically, you can see a slow trend of decreasing chlorophyll A, that's nice. However, we're not seeing any improvement of elevating the dissolved oxygen in deep pocket, deep water. That is after point source control. This is point source control. So, the state of Maryland decided to, let's do something. There's something, of course, you know what's coming up. Non-point source control, watershed. Naturally. Now, we asked model, can we do it? Okay. We asked the model. The model, we built this model from scratch. It's a mesh between C equal and the W2 model. W2 is vertical layer model. C equal, of course, is one dimension. I'm talking about the merging of kinetics. Let's see. Yeah? Then we call it W2 neutral. W2 neutral. Why do we use this name? The neutral is the neutral part of another commonly used model called WASP. So this is moving up to the WASP level. Notice here we call it zero order SOD, sediment oxygen demand. That is, we need to assign the sediment oxygen demand. But then when we move on, we put in, can you see this? We put in a diagenesis model. Diagenesis is like a cooker, converting back from organic nutrients back to inorganic nutrients. Diagenesis, this is what diagenesis. This is sediment-water interface. Sediment has two layers. This is aerobic, this one is anaerobic. And we have all these processes. They're all in there now. Let's look at the model. This is the top layer, 2 years worth of data. Actually, 1, 2, 3, 4, 5, 10 dates, from 97 to 99. Of course, I only present you the nice, the good ones. But they are good, actually. Now, this is Nottingham. You see, historically, that's Nottingham, grow algae. Model result was matched data, compared with data. Dissolved oxygen, but the bottom. The same days, corresponding same day. Oh, good. Summertime, June, July, we matched it, the bottom. We picked up the bottom. Okay. Even more rigorous comparison, dissolved oxygen. Many days of 2 years, but instead, this is vertical now. You can see that summertime, the vertical, the bottom, dissolved oxygen. I hope you can start appreciating the availability of data. Yeah. Now, chlorophyll A top layer, let's use the model to do some analysis. given the fact that, okay, we consider the model is calibrated and validated, we run the model continuous. This is real time. It's not steady state. Real time, two-dimensional. Continuously. And got verified. And then now we ask model questions. Current condition, load increase, load decrease, very responding, you see, for chlorophyll A. That's not surprising. That's what we experienced earlier. See, when we look at dissolved oxygen, well, not so on current condition, but until we change this downstream boundary condition that we can have. That means we end up with boundary condition, the mouth. The mouth is going into the Chesapeake Bay, controlling this. That's bad. Why? Because that's uncertain. That's one uncertain. We cannot project, cannot predict. I'll explain to you the boundary condition further. Now, calibrations of water quality, this is expanded shots. Chlorophyll A, this, you're looking at 2 years now. One way we can do this is a 100 kilometer long estuary, although the low dissolved oxygen is located in the downstream area. Let's see, this is an interesting result. After this, you start appreciating the hydrodynamics come into play. This is a 2-year hydrograph. The fresh water going into the estuary, at the head of the estuary. That is when the water, there's no tides. Flows, cubic feet per second. August, September, October. This is spring. Okay? And this is summer, June, July, August, September. Typical in mid-Atlantic climate. Springtime, so we always call it April shower. Springtime, we have more rain. It so happened that in this 2 years, continued 2 years, one, this is wet year, the other one is dry year. The other year, see, spring, much lower. That gives us even more interesting results. But this is data, this is all actual data, we don't mess around. Comparison of loading scenarios here. This is percent volume field less than 2 milligram per liter. Less than 2 milligram per liter. Remember, this is 100 kilometer long. And the segment, overall, we chopped up this into 160 some segments, longitudinally. How about that? Vertical? Well, depending on the shallow or deep. We always keep constant depth, 1 meter layer. The deep part has over 30 layers. Okay, that's how the two-dimensional structure is. Every instant, the model spit out results. We collect them, look at the dissolved oxygen level in each of the total. You know how many boxes? We have 2,000 boxes. And you don't do it by hand, of course. Collect the deal information. If it's below 2 milligrams, okay, you pick it. We know the volume of each box. Add up the box volume divided by the whole estuary. That's called the percent volume with 2 DO below 2 milligrams per liter. Let's see. In the summertime, yeah, we have some. In the wintertime, of course, nothing happens. No problem. This summer counts. Yeah, this summer counts. Okay. Now, we have 3 curves here. Baseline, load increase, load decrease. They're almost identical. You see? They're almost identical. So the load decrease doesn't help much. Then, okay, we accept, and we'll look at it widening down the road. But interestingly is that this area is bigger than area. Why is that? Well, this is high flow season. Upstream, all fresh water. Downstream, go this way, tides, right? And then, of course, we have many, many layers in the model. What I'm saying is, high flow creates a strong shear, cutting. The high flow cut off the oxygen resupply from Mother Nature, from atmosphere. That's why situation is worse here than there. Now you see hydrodynamics come into play. Now, so this is disappointing. The load increase doesn't help. So now we have we bring in another variable. The downstream condition is the downstream condition, boundary condition at the mouth of this. If we change the boundary condition vividly, we have very good response. You see, this has become very low, right? How do we interpret these results? How do we interpret these results? Let's see. We have asked the model a number of questions. To what extent nutrient loads from? We will ask the model all these questions. Let me back up a little bit. Explain this. This is what is downstream boundary condition mean? Estuary, upstream coming down here, downstream. Downstream boundary condition set here, right? Well, what is the qualification of boundary condition? Upstream, that's no problem. Upstream has no tide. So the boundary condition from upstream, it's only affecting this. Right? But downstream here, we have tides. We have interchange here. Okay? So this boundary condition, particularly, they will bring stuff coming into the estuary here. So the problem is, what the last slide showed you that the boundary condition, unfortunately, is affected by what's going on inside the system. What's going on means load reduction, load increase. It's affected here. Okay, you're not qualified as boundary condition. I'm sorry. You know, boundary condition is like earlier said, big elephant leg. You cannot shake it. You cannot be affected. If it's affected, you're disqualified as a boundary condition. But we can't help. That's the way it is. Unless we move the boundary all the way out here to the Atlantic. That's the problem. So that is the problem. More interpretation of this, the disappointing outcome is, this is the Patuxent. We set the boundary condition here for model to run. Like I said, it's not well qualified. So we have to set the boundary condition outside here. Huh? Of course we can do that. Yeah. Technically, that's not a problem. But that's not the point. The point is, remember, we want to do water quality management. So the idea is, we're going to cut the non-point source watershed farmers' nutrient loads. But it won't work. Why is that? That is, it's controlled by the boundary condition here, which we set the boundary condition. That also means, let's use more general terms, easier understood terms. Is, for example, your neighbor, they dump into the bay. At this point, still tidal. So the dump is here, was shifted to the dump here, from step. So you clean up your house, good. But your neighbor dumped the trash in front of your house, useless. So what it matters is we have to do this entirely, which, of course, later on I'll show you. We do have a Chesapeake Bay model complicated model. But the Patuxent eutrophication does not end here. Let's say, since we have the model calibrated, let's look at some other information. See if we squeeze the model for more physical insights. Okay. To what extent nutrient loads from the watershed contributing to the total loads? Chesapeake Bay a nutrient source for the Patuxent, since we apply it's in and out, right? It's good to ask this question because that's important. If the Chesapeake Bay is a source, then you're cleaning up inside, it's useless. How significant is the role of sediment in the overall nutrient budget? Where and when is nitrogen phosphate limiting the algal growth? Do the spatial pattern of limiting nutrients change between wet and dry years? So these are next level of questions. Now we have a calibrated and validated model. We can ask the model. To summarize this is a little complicated, but it's extremely interesting and important. We call it, this is an interplay of model results and the data, interplay. This is phosphorus. Phosphorus. We look at phosphorus limitation, budget, and dynamics. Phosphorus, 2 years, 0 to 120 days. This is phosphorus limitation. Remember, that is that phosphorus that takes that nutrient. That number is only between 0 and 1. Between 0 and 1. 1 means no limitation. Plenty of food, plenty of phosphorus for the algae. Yeah? Next one is orthophosphate concentration. The food, the concentration. Where? At the mouth. Okay. Next one is phosphorus loads. These bar chart continuously is the watershed load. Source load. This little dot here is how much loss into the bed. Remember, this is net loss. Always a dynamic exchange, two-way traffic. Okay, but the net is always go down. That's why we accumulate the stuff down there, right? The net accumulation. Now this is phosphorus loads, net phosphorus loads to the Chesapeake Bay. Okay? Seasonal pattern of net exchange. Closely follow that of phosphorus load. See, you have a 0 line here. 0 means net is 0. Positive means there's phosphorus going into the bay. But this is dynamic, over a 2-year span. Negative value means, we got phosphorus coming in from the bay. All this can be calculated from this verified model. But you look at the dynamic pattern here, very similar to these bars. Conclusion, strong influence of watershed loads at the mouth. So the mouth for phosphorus situation is strongly influenced by the watershed, not by the mouth. Over a 12 months period, net loss are positive. That means delivering phosphorus loads to the bay. Here comes into interesting phosphorus limit situation at Nottingham. We have two curves here. Nottingham is the top one. The other one is Brooms Island. Remember, Nottingham is upstream. Brooms Island is downstream. Nottingham, orthophosphate about, let's take a look at this. Yeah. This curve, this straight line is the 0.001. That is earlier when we talk about, that's this one. This concentration is 0.001 milligram per liter. Milligram per liter, very small, very small. Now, very close to all these, and No, the question, let me back up. What is the question? The question is, why in the first year, in the wet year, there's no limitation for phosphorus at Brooks Island, yet there is significant one in Brooks Island. Yet their concentrations are very similar. Huh? Similar what? Concentration at the outside of the river, that's at the mouth. Between that and the earlier rationale here, we call that Brooks Island occurred only in winter of 1999 is due to the watershed law, because the watershed here mimic these two. I know this is a little bit really complicated to comprehend, but that's okay. My point trying to cross is we can use the model to extract lots of results. And all of these conclusions directly affect our morphology management. We're not doing this for fun. We're doing this for good use. Nitrogen, different. Nitrogen, Nottingham got this. That Nottingham is upstream. Why we have low here? Huh? That's summertime. Brooks Island, now, look at these two. Again, for one thing, you have to realize that this is metric, this is milligram, or 1 metric ton, milligram per day. Look at the scale 120. That's nitrogen. For phosphorus, 6. Okay? 20 to 1. That's the situation. Again, nitrogen, basically the message tells us is totally different picture. Watershed is not the controlling factor. Instead, this limitation is controlled by the valves, by the valves. Okay? So that's the, right now, let's stop this a little bit. I can show you a how do I stop this? And downstream. The top is Caulfield entire estuary. In two-dimensional. This direction and this direction. The bottom is dissolved oxygen. Okay? This is the timeline, you can see that. Now, the wintertime, dissolved oxygen is blue. Nice, right? Pretty good. And nothing happened. Now starting, have some algal growth there. All right, see, summertime, starting summertime stratification. You see that? Stratification, strongly stratified. Now, this is summertime. This is the hydrograph. Yeah, that still have strong. See, the algal growth peak always there. The peak, right? Oh, quiet down. Winter time, cold, quiet down. Quiet. That gives you the date. March, late March. Yeah, still growing here. Now, stratification starts. Does DO stratification only deep area? Very severely stratified. Try again. Do it again. See, the date's changing now. See, in the winter, the whole thing is quiet. No problem with oxygen. This whole thing was my PhD student thesis in 2007. Actually, this is only part of the thesis. The continuation of this is modeling of copper and arsen. I have the problem here, I can leave it with you, but in the interest of time, we may not have opportunity to go over. Because let's skip that, because I have to give you another 5 minutes. This is Potomac Estuary. This is Nations River. This is much bigger than the Patuxent. Same problem. I go this quick. The problem, phosphorus. And another unique problem here, blue-green algae. Blue-green algae deflects nitrogen from the air. So controlling nitrogen is no use. But, at wastewater treatment plants, we reduce nitrogen loads, is no use. They can get the nitrogen from up in the air. So, they focus on phosphorus control. Now, you can see, phosphorus load, 1910, 1930, 40, since 40, sharp rise. Why? Well, since after World War II, the phosphate detergent will be heavily used. Okay, so in 1970, reached very high. The EPA decided, US EPA spent $1 billion on the wastewater treatment plant around this area to do phosphorus removal. Very successful, down to the level of less than 0.2 milligram per liter total phosphorus. There's as much you can do. There's not much you can do, not other things you can do, because concentration in the river here is 0.67 milligram per liter. And if the wastewater treatment plant discharge less than 0.2, what can you do, right? So also mean that the 0.67 upstream, that's what? Not consumes. All right, so reduced, $1 billion spent, reduced, fine. And then the blue-green algal group gone. Everybody happy. But in the summer of 1983, it was extremely hot. Suddenly, blue-green algal group returned, as never happened before, like a big storm.
So at the same time, the Great Lakes were also, in the Great Lakes also the same thing happened, I guess.
Yeah.
So around the same time.
Yeah, but Great Lakes control started earlier.
I see.
Yeah, this problem is 1983 problem.
I see.
Yeah. So we did have a model to guide control, guide the management. So $1 billion spent. EPA was very nervous. They formed a committee to investigate. Everybody asked the same question, right? Everybody asked this question. How about there must be excessive nutrients in the water. Where's it from? They point a finger at the wastewater treatment plant, maybe a malfunction. No, this record is all public. I said it's less than 0.2 milligram per liter. No problem. The 5-person investigation panel, led by expert on water quality modeling, Tolman. I don't know if you have read his book. Tolman. He developed the original model. So he headed up that investigation. He said, why don't we ask the model? Just like the other thing I did for the Patuxent, right? Ask the model, throw the bricks for the model. Okay. So we ran the model, feed the model with the 1983 summer data, right? All these are public. So watch this here. Chlorophyll A, these dots are data, upstream, downstream. Just look at the solid line curve. That is the model. Model failed to match these data, right? Failed. How about dissolved IP, inorganic phosphorus? These are the data. The model come down with it, hit 0. You see, it's not model's fault. Model said, I don't have food. How can I grow? Right? Makes sense? Models don't lie in this situation. Same thing in total phosphorus. But interesting, in dissolved inorganic nitrogen, they need both phosphorus and nitrogen, right? It's the other way around. The solid line higher than the data. That gives us a really good clue. This is so powerful, interplay of modeling results and the field data. This powerful message is, what if we find that extra phosphorus source that feed them? It will grow more algae, and when we grow more algae, it needs more nitrogen, right? So the nitrogen should come down. Now the model stand ready for that. The model said, we can ask the model, all right, put an extra poundage of model out, put extra number. Finally, the model said, well, I need this much. That much put in, much improved, interesting, much improved. So now the question becomes, how do we find this extra? Very interesting. From chemistry, we know that under anaerobic condition, in the water column, iron, a lot of species release, right? Phosphorus is one of them. Is that anaerobic? No. Chlorophyll up to that high level, the entire water column from top to the bottom supersaturated with oxygen, right? Because algae release oxygen, right? Photosynthetic. So that clue doesn't work. Must be from somewhere. But they did notice something. The pH went up really high in that period to 12 or 13. That's not usual. That's really unusual. You have chemistry. What is the pH range in natural water between 6 and 9? Because Mother Nature gives us buffering capacity, capability to battle against acid, to battle against alcohol. Okay, how pH get up to 12? That's another question. Let's see. Out of the inside the 5-person panel, there's one sediment specialist. So they got the sediment data back into the lab. Deliberately they jack the pH up to 12 or 13 and try to measure. Sure enough, phosphorus flux was measured. It's right in this range. Right in this range. That's really something. Now, we call that as a hidden mechanism. How to explain this? It's anaerobic, this is typical. 2-layer. This aerobic, this is aerobic layer, and this is phosphorus. This is oxygen greater than 0. Here, oxygen anaerobic, and we do have certain absorption so that trying to hold on it with the pH normal, less than 9.5. We do have flux, but we'll hit a wall here. Now, anaerobic typically, dissolved oxygen is 0. The whole thing is dissolved oxygen is 0. Strong release. In the Potomac 1983 case, pH much higher. This absorption does not exist. No absorption. That's why. Release. It turned out this is a great finding of our chemistry. That panel, their work published in the paper, they earned the EPA's Best Science Award in the following year. It was a major achievement. So that is what is interesting. So mechanism not included in the model becomes significant after some level of treatment. That is this. It is critical to review the model performance. Finally, you can say that still subject to some uncertainty of missed or hidden mechanism we did not know. We cannot 100% say this model is totally verified. No. We learned this. Now, back to that boundary condition. Earlier, the Chesapeake Bay model, this mechanism. Patuxent, here. Potomac, this one. All this is two 20,000 boxes. And they could only run this model on a supercomputer. Earlier, this is the mouth. This is the mouth. No. It turned out the same idea. This is not qualified. They have to move out to continental shelf. This is land, right? This is the boxes. This is land, boundary. This is ocean. This is ocean, this is ocean. Pushed all the way out here, it's staying like a big elephant. It would not change. So any changes inside would not affect this here. That's the final version of this big Chesapeake Bay model. And they quickly realized it's abandoned. Okay. So that's pretty much, we have some takeaway points. Data support critical monitoring. Post-audit essential. Recheck the model. Science to advance. Modeling, not learning models.